Hello everyone, my name is Sian, and today I'm very glad to have this opportunity to share with you some of our recent research accelerating parallel write via deeply integrating predictive lossy compression with HDF5. So we know that nowadays large-scale scientific simulations can generate extremely large amount of data. So some of them you can see on the right-hand side figure. However, these large amount of data is limited by the storage and I/O bandwidth for large-scale parallel computers nowadays, especially when you compare the storage system to the computing power of these supercomputers. And this kind of storage and I/O bandwidth can be a bottleneck for the simulation. And lossy compression is one of the most efficient way to reduce this data to improve the overall performance because of its high compression ratio, especially when you compare it to the lossless compression, and also because of its controllable compression error. And typically we will use the I/O libraries such as HDF5 to do the parallel write for the scientific data management. And the parallel write HDF5 support compression filter to reduce the data size and improve I/O performance. However, the current implementation of the parallel write still has some limitations. Mainly is that the compression and I/O are sequential to each other, so which means the I/O has to wait until all the compression to be finished and then start the I/O. And also, because of the compression size of each partition is distributed across a wide range of bit rates or compression ratios, you can see on the right-hand side this figure demonstrates that the compression ratio or the bit rates are distributed across a wide range. And this causes that the offset cannot be simply pre-assigned for the compressed data. So in this research, our solution is to integrate predictive lossy compression with the asynchronous I/O. To do that, we first extend the prediction model to not only estimate the offset, but also the performance of parallel I/O. And then using that information and our specific design, we overlap the I/O with the compression. And in the same time, we also optimize for the reorder compression tasks to achieve even higher overall improvement. So our solution improves the parallel write performance by up to 4.5 times compared to the original, and by up to 2.9 times compared to the solution with SC lossy compression filter, with only 1.5% storage overhead. And so before we jump into our design, let's look at some of the backgrounds. So first of all, as mentioned, the parallel I/O libraries for HPC applications are widely used to access and manage the scientific data efficiently and to move the data between compute nodes and storage. And previously, the compression is just one dedicated layer in between the application and I/O libraries. As shown in the right-hand side, you can see the blue areas is the previous solution where compression is just a dedicated module. And this will cause an overall lower compression and write efficiency. Recently, HDF5 team has proposed the virtual object layer called VOL to redirect the I/O operations into VOL connector and allows asynchronous I/O. So we will also leverage these features in our research. And there are two I/O intensive HPC applications that we use and targeted for in this paper. The first one is NICS cosmology simulation, which is a hydrodynamics code designed to module astrophysical reaction flows, and it supports MPI, OpenMP, CUDA, and is also very large scale. And another is VPIC, which is a vector particle in cell simulation for plasma physics. And both of these scientific simulations can generate an extremely large amount of data for dumping and to write to the storage system. And on the other hand is the error-bounded lossy compression. So there are some terms that we need to understand. The first one is the compression ratio, which means the ratio between the original and compressed data size. Sometimes we also refer to the bits rate, which is the average bits to represent each value. Another is the data distortion, which means the reconstructed data quality compared to the original, and also the error bound. So the error bound is to ensure the difference between original and reconstructed data to not exceed this user-specific error bound. So and combined with error distortion, this is the error control for the error bounded lossy compression. And the fundamental principle for the prediction-based lossy compression is that each data point's value is predicted based on its neighboring data points. And then we will do a linear scale quantization on the difference between the predicted value and the original value. So you can see on the right-hand side. And then we will use various encoding techniques to encode this data, including Huffman encoding and also another layer of lossless compression to improve the overall performance of the compression. So let's look at our proposed design. On the left-hand side, this is an overview of our proposed solution. So you can see this illustrates 4 processors, and for each processor there are several steps. The first one is to predict the compression ratio, etc., for each data partitions and each data fields. And then an all-gather operation will exchange this information across different processors. And then after each processor get this information, they can compute the offset for the parallel write, and then the optimization for each processor to reorder the compression sequence of different data fields, and then we can overlap the compression and I/O for each processor. After which we do another all-gather operation to exchange the data overflow information and then handle the overflowed data. And then we can look at this figure, the timeline figure, to demonstrate how we improve over previous solutions. So in this figure, there are 5 processors, and each processor will hold 2 data fields. So you can see the original solution will just write the data to the storage system, which is all pink. The pink in this figure demonstrates the I/O time, and the gray bar is the compression time. So you can see the previous solution to use lossy compression as a filter is that each processor will have to wait until the slowest processor to finish its task to start the next task, the I/O or compression. And our solution can overlap the compression and I/O. This is a big improvement compared to the previous lossy compression with collective write. And then furthermore, we also reschedule the compression order. This will further improve the performance compared to previous one. So let's look at some of the details of our design methodology. First of all is the compressor throughput estimation. So on the right-hand side, you can see this figure. We evaluate the compression bitrate with the compression throughput across different data set and data fields. And you can see they show a very stable relationship between the throughput and the compression bitrate. Also on the left-hand side, we demonstrate that the min-max of the compression throughput are similarly bounded across different data samples, in this case from different partitions of the NIC simulation. So using those information, we can actually form a formula shown in this page to estimate the compression time of lossy compression. Similarly, we also formulate the write time estimation. On the right-hand side, you can see this demonstrated that the different data sites per process compared to the throughput of that configuration. So in this case, you can see when the data size per process is extremely small, the throughput is actually not very stable. However, in our research, we mainly focus on the relative write time across different data sizes instead of the exact write time of each process. So we simplified our model and use the following equation to to estimate the write time. So using those information, we can actually overlapping the compression with write. So first of all, we estimate the offset based on the predicted compression ratio. Note that this predicted compression ratio is not 100% accurate compared to the actual compressed size. So the actual compressed size can be either sometimes larger, sometimes smaller than the predicted value. So you can see on the right-hand side, after the original data being predicted into this blue bar representing for the predicted compressed size, we actually reserve this pink bar, the extra space, is reserved for unpredicted compressed data overflow. However, in some extreme cases where the actual compressed size can be still larger than this reserved area, we will actually write this overflowed data into the end of the shared HDF5 file. So you can see there is actually a balance between the extra space size and the performance overhead. So if we assign a very large extra space, then the extra space overhead can be very large. However, if we assign a very small extra space, then the overflow data can be very frequent and the performance overhead will be enlarged. So based on our evaluation on the right hand side, this figure demonstrated is a comparison between using different extra space ratio and the performance overhead and also the compression size overhead. So we determined that the default at the extra space ratio should be default at 1.25 for most partitions. And also for some partitions with extremely high compression ratio, we adjust this extra space to a slightly larger value because those with very high compression ratio, the reserved area is very small, and even though we assign a slightly larger extra space, it will not have any impact to the overall compression size overhead. However, it will greatly improve the performance overhead. And then for each process, we can actually do the compression order optimization to improve the overlapping efficiency. So is that the I/O of each partition happens after compression, and we want to avoid unnecessary wait time for I/O. So what we can do is to reschedule the compression sequence of different data fields on the same process. So on the right-hand side is the procedure code of our optimization. And this optimization is very suitable when the compression time and I/O time are fairly similar to each other. However, there are some limitations for this optimization. In the following two situations, this optimization will not provide too much of improvement. One is when the compression time is significantly shorter than the I/O time. Another is when the compression time is significantly larger than the I/O time. You can see on the left-hand side this figure. Even though we can adjust the compression sequence of the two data fields, it will not make too much difference. So let's look at some of the evaluation results. First of all is the evaluation setup. We implement our approach with HDF5 and SA3, which is a modularized prediction-based lossy compressor. And we implement our evaluation on 2HPC system and with different scale of NICs and VPIC datasets. And in the following evaluation, we use PSNR to validate the reconstructed data quality. And if not specified, the compression ratio is targeted at 16 times. And here is a chart that demonstrates the datasets that we use in our evaluation. You can see the largest dataset is 4.62 terabytes, which is very large for a single snapshot. So first is the accuracy of compression and I/O throughput estimation. So on the right-hand side, these two figures are the compression throughput estimation on two different scales of NIC simulation datasets. And the red lines are the estimation and the black dots are the actual data points. Similarly, on the left-hand side is the I/O throughput estimation using our solution. So we can see from those figures, we have a very high accuracy on compression time estimation with different partitions and different data scales. And also we can provide a high accuracy on write time estimation. Now note that we have some distortion on the write time estimation, but this will not affect our optimization based on our previous discussion. Next is the evaluation on extra space ratio. So we mentioned that by tuning the extra space ratio, there is actually a trade-off between the performance and the storage overhead. So we look at these two figures are done on two datasets, NICs and the VPIC datasets on both machines, Bebop and Summit, and of course they have multiple data fields, and we find that the trade-off curve between performance and storage are highly similar. And by lowering the extra space ratio to a certain point, in this case 1.1, this will result in an extremely high performance overhead. So we can use the same extra space ratio for different setups, and we use the default at 1.25. And of course, users can also custom the extra space ratio. Next, let's look at the overall performance evaluation. So we mainly compare using 4 solutions. The first one is the original solution, which is a non-compression solution. Just write the data to the shared file. And the next one is the previous solution, which is using the compression filter solution. And the third one is the overlap solution, which is our proposed solution. And we also adding the reordering solution, which is our overlapping solution plus our reordering techniques. So if we look at the right side, this figure demonstrates that compared with the original solution, the previous solution can provide a 1.87 times performance improvement. And then compared to the previous, our overlap solution can provide a 1.79 times performance improvement. And then adding our reordering techniques, we can further provide a 1.3 times improvement compared to just overlapping. So overall, we have a 2.91 times improvement from previous with 26% storage overhead, and it's just actually 1.5% if compared to the original data sets. And it's stable performance over different time steps. So you can see on the right-hand side, we actually demonstrate multiple time step of the next data sets, and our improvement is very stable. And next is the performance with different overall ratio. So we know that we can compress the data into different bit rate or with different compression ratio. So we evaluated that with the 2 data sets we have, the NICS and VPIC data sets. So this figure demonstrates that when we use different overall ratios, the performance improvement compared to our solution and the previous solution. And in these figures, the red dot line are the original write time. So we find that limited improvement from reordering optimization under extremely high and low bit rates, which for both of the cases are because of the I/O time and the compression time are extremely imbalanced. And as mentioned before, in this case, the reordering optimization will not provide too much improvement. And the storage overhead is very stable across different overall ratios. And we also find that the performance improvement over previous is more significant towards higher bit rate. And this is because in the lower bit rate, the compression time is actually domains the overall write time, and with very little overlap efficiency. And next, we also compare the performance with different scales. So we use the same compression ratio for these tasks and done on both NICS and VPIC datasets, but with different scales. And similarly, we compared our solution, both reordering and overlapping solution, to previous solution. So we find that the improvement from reordering optimization is very stable, and the storage overhead is also very stable in this case. And the performance improvement over previous is more significant towards larger scales. And this is because the asynchronous write typically will provide a better scalability compared to the collective write used by previous compression and the write solution. So in conclusion, in this paper, we first extend the prediction model to estimate the offset and performance of parallel I/O. And using that techniques and our specific design of extra space, we can overlap the I/O with compression. And furthermore, we improve the overall performance by optimizing the order of the compression tasks. So our solution improves the parallel write performance by up to 4.5 times compared to the original and 2.9 times compared to the previous solution with only 1.5 storage overhead. So some of our future works includes that first, we would like to implement our workflow onto more I/O libraries. And also we would like to test with more scientific applications with various backgrounds and various post-hoc analysis. And also we would like to investigate that if we use application-specific post-hoc analysis, we would want to adjust the compression configurations for different partitions or different timestamps. And in that case, how should we adjust our solution to fit the in situ compression purposes? And that's all. Thank you very much.